The intellectual odyssey rages on. Quantum mechanics unveils a captivating realm where particles behave as both waves and particles, defying our classical intuitions. Within this enchanting framework, quantum numbers emerge as the keys to unlock the intricate patterns and symmetries of atomic orbitals, revealing the mesmerizing beauty hidden within the microscopic world. Let me take you to this beautiful journey into the quantum mechanics. But first, like, share, subscribe to my channel from many phones. Classical mechanics, formulated by Newton's laws of motion, effectively describes the behavior of macroscopic objects like falling stones and orbiting planets. However, when it comes to understanding the intricate nature of microscopic particles such as electrons, atoms, and molecules, classical mechanics falls short. Enter quantum mechanics, a revolutionary theoretical framework that embraces the dual behavior of matter and the uncertainty principle. In this essay, we will embark on a captivating journey through the quantum mechanical model, exploring its application to atoms and shedding light on its profound implications. Quantized energy levels. One of the defining features of the quantum mechanical model is the concept of quantized energy levels. Electrons in atoms can only occupy specific, discrete energy states. These quantized energy levels, derived from the wave-like properties of electrons, emerge as solutions to the Schrödinger equation. They represent the only permissible states for electrons within an atom. Uncertainty principle. In the realm of quantum mechanics, the uncertainty principle asserts a fundamental limit to the simultaneous knowledge of certain pairs of physical properties. For instance, the precise determination of an electron's position and velocity within an atom is inherently uncertain. This realization leads to a profound shift in our understanding, as we can only speak of the probability of locating an electron at various points within an atom. Atomic orbitals. To describe the behavior of electrons within atoms, we employ mathematical functions known as atomic orbitals. These orbitals are intimately connected to wave functions and provide insights into the electron's distribution within the atom. Each atomic orbital corresponds to a specific energy level, and has the capacity to accommodate a maximum of 2 electrons. In multi-electron atoms, electrons populate various orbitals in order of increasing energy. Probability density. Central to the quantum mechanical model is the notion of probability density. The square of the orbital wave function, denoted as psi vertical bar 2, represents the likelihood of finding an electron at a specific point within an atom. This probability density, always positive, allows us to predict regions around the nucleus where electrons are most likely to reside. It provides a comprehensive understanding of the electron's distribution within the atom. The hydrogen atom, and the Schrödinger equation. When we apply the Schrödinger equation to the hydrogen atom, a remarkable solution emerges. This solution reveals the possible energy levels that electrons can occupy and the corresponding wave functions associated with each level. These energy states, characterized by quantum numbers such as the principal quantum number, n, azimuthal quantum number, L, and magnetic quantum number, ML, form the basis of the hydrogen atom's behavior. The quantum mechanical model surpasses the limitations of the earlier Bohr model and successfully explains the spectrum and phenomena of the hydrogen atom. multi-electron atoms. While solving the Schrödinger equation exactly for multi-electron atoms proves challenging, approximate methods and computational techniques come to the rescue. These calculations demonstrate that orbitals in atoms, beyond hydrogen, exhibit similarities to hydrogen orbitals. However, the increased nuclear charge leads to orbital contraction. Furthermore, in multi-electron atoms, orbital energies depend not only on the principal quantum number, n, but also on the azimuthal quantum number, L. Let me take you to quantum numbers now. In the fascinating world of quantum mechanics, atomic orbitals are defined by a set of quantum numbers that provide insights into their size, shape, orientation, and energy. These quantum numbers, namely the principal quantum number, n, azimuthal quantum number, L, magnetic quantum number, m, and electron spin quantum number, ms, paint a vivid picture of the behavior and characteristics of electrons within atoms. In this essay, we delve into the significance of these quantum numbers and their role in defining the intricate nature of atomic orbitals. Principal quantum number, n, the principal quantum number, denoted as n, is a positive integer, n equals 1, 2, 3, etc., that determines the size and, to a large extent, the energy of an orbital. For hydrogen and hydrogen-like species, the energy and size of the orbital solely depend on n. As n increases, the size of the orbital expands, moving the electron further away from the nucleus. Additionally, higher values of n require more energy to remove the negatively charged electron from the positively charged nucleus, resulting in increased orbital energy. Azimuthal quantum number, L, the azimuthal quantum number, also known as the orbital angular momentum or subsidiary quantum number, is represented by L. It defines the three-dimensional shape of the orbital. For a given value of n, L can range from 0 to n1. In other words, for a specific n, the possible values of L are 0, 1, 2, up to n1. Each L value corresponds to a subshell within a principal shell. The different subshells are represented by symbols such as S, P, D, F, and so on, according to their L values. Magnetic quantum number, m, the magnetic quantum number, denoted as m, provides information about the spatial orientation of the orbital with respect to a standard set of coordinate axes. The number of permissible m values for a given subshell, determined by its L value, is given by 2 liters plus 1. The range of m values is given by L-L, 1, L, 2, 0, 1, L, 2, L, 1, L. Each m value corresponds to a specific orientation of the orbital in space. For example, n's orbital, L equals 0, has only one permitted m value of 0, while a p orbital, L equals 1, has 3 permitted m values: 1, 0, and 1. Electron spin quantum number, ms. To complete the description of an atomic orbital, we introduce the electron spin quantum number, ms. This quantum number accounts for the intrinsic property of electron spin. An electron can have one of two possible spin states, plus half, spin up, represented as, or minus half spin down, represented as. When two electrons occupy the same orbital, they must have opposite spin states, following the Pauli exclusion principle. This additional quantum number plays a crucial role in explaining observed line spectra, especially the presence of doublets and triplets. Quantum mechanics, with its elegant mathematical formalism and intricate interplay of quantum numbers, unveils the hidden beauty of the microscopic world. The quantum numbers, like celestial coordinates, guide us through the mesmerizing dance of electrons, revealing the harmonious symphony of size, shape, orientation, and energy within atomic orbitals. They invite us to witness the enchanting tapestry of nature's quantum realm, where the laws of physics weave an intricate and awe-inspiring masterpiece. I hope you enjoyed this, didn't you? The intellectual odyssey rages on. You can find more interesting chemistry videos on my channel.